Hello AP Statistics students. In this video, we're going to continue looking at two-sample, two-proportion z-interval scenarios. With a slight twist, though. They are just a tiny bit different when you're using them to look at the results of an experiment. And so we're going to look at some of those slight differences. They're not that bad. There's actually, I think, just a few things you don't have to do and a few wordings that are important. Mostly this will just give us more practice at doing a two-sample z-interval for P1 minus P2. So let's take a look at how to do this. So here's our scenario. Patients with lower back pain are often given non-steroidal anti-inflammatory drugs, NSAIDs, like Naxaprin, to help ease their pain. Researchers wonder if taking Valium along with naproxen would affect their pain relief. To find out, they recruit 112 patients with severe lower back pain. Whew, sign me up. And randomly assign them to one of two treatments, naproxen and Valium, or naproxen and a placebo. After 1 week, 39 of the 57 subjects who took naproxen and Valium reported reduced lower back pain, compared with 43 of the 55 subjects in the naproxen and placebo group. All right, so there's our scenario. Hopefully you can see that we have two populations here. We're going to have two proportions, and we want to see the difference between the two proportions. Construct and interpret a 99% confidence interval for the difference, and here is our context, right? In the proportion of patients like these who would report reduced lower back pain after taking naproxen and Valium versus after taking naproxen and a placebo for a week. And then, of course, we ask ourselves, do we have convincing evidence? That is part B of our conclusion here. So let's do this. Again, we have a 4-step procedure, right? First, to figure out why I can't, oh, that's as far down as it goes. All right, so step 1, we have to state, right? What are we doing here? So we are doing a 99% confidence interval for P1 minus P2. Oh, I want to stay in that. Where P1, that is not working the way I wanted to. Oh well. Where P1 is can't get out of the equation. There we go. Where P1 is the proportion of, all right, I'm just going to grab the context from the question, right? But it has a few important points. Patients like these who would report reduced lower back pain after taking naproxen and Valium, and P2 is the proportion of patients like these who would report reduced lower back pain after taking naproxen and a placebo. Whew. Nice and long, but mostly that is all just straight context from the problem, right? Basically, we're just saying, hey, we're doing a 99% confidence interval for P1 and P2. Then we have to say what P1 and P2 are, all right? We have to label our variables. Now, a couple of important things in that sentence that might not seem like they're important, all right? Patients like these, okay? I put that in both of the patients like context here. That is important because you want to make sure, because you're talking about P1 and P2, these are population proportions. You don't want to say patients that have had the surgery, because we are trying to generalize this to people who might have this surgery, or sorry, this experiment. It's not surgery in this case, is it? It's just these drugs, who might take these drugs in the future. So you don't want to say patients that have taken these drugs. That makes it sound like you are talking about the subjects in the study if you say that they have taken it already. You want it to be patients like the ones we've taken, like these that we have in the study, who might take it later. It's also important to note the population here is patients like these because we did not randomly select these subjects. Okay? These subjects were not randomly selected. They were, didn't it say recruited? They were recruited. They were not randomly selected, which means we can only generalize the results of this experiment to patients like these. Okay? If the people we recruited had a certain characteristic, that is kind of important, like back pain. All right, what if these were all office workers? Okay, and we got the results for this experiment about office workers. Well, we wouldn't necessarily want to generalize these results to construction workers, right? So I hope that makes some sense. We do want to include that patients like these. It kind of does two things there for us. It tells us who we can generalize this to, and it makes sure that we're not talking about the sample, people that have already had the treatment, whether it's surgery or drugs or whatever it is. All right, so that's why the patients like these is kind of important. That's one difference with experiments that we didn't have to worry about before. All right, we did the state. Time to plan. All right, so what is our plan here? Well, we are doing a 2-sample Z interval for P1 minus P2. All right, that is our procedure here, right? That's what we plan on doing, a 2-sample Z interval for P1 minus P2. Now, are we allowed to do this? So first, our random condition. Now you might think, oh, Bolt, didn't you just say that they didn't randomly select these people? True that, all right? You never randomly pick people for an experiment. That's not how experiments go. To satisfy the random condition for an experiment, we randomly assign participants to treatment or placebo. All right? The subjects were randomly assigned to the treatment or the placebo. So yes, check mark, we do have the random condition. All right? And I'm assuming it said somewhere up here that they were randomly assigned. Yes, right here. They are randomly assigned to one of 2 treatments. All right, next, the large counts condition. All right, do we have big enough, I don't want to say sample sizes, but do we have enough people? So the same idea here applies. Do we have 10 successes and 10 failures? So for treatment 1, we have, what was it, 39. All right, this is from our results. These are the successes. 39 said that they did report reduced back pain. So we have 39. And then the number of failures would be 57 minus 39, which is 10, 11, 18, which those are both greater than or equal to 10. And for treatment 2, all right, what was treatment 2? I forgot. 43, all right, so 43, that's bigger than 10. And if there were 55 total there, so 55 minus 43, I believe, is just big enough. That is 12, isn't it? Which those are both greater than or equal to 10. So remember, we're looking at successes and failures here. They didn't give us a proportion, so I don't have to do n times p. N times p would be 39, and n times q would be 18. It's just the successes and the failures. Boom. Large counts means our sampling distribution would have been, is normal. Now you might be thinking, bolt. You forgot one, man. What happened to the 10% condition? Well, that's one difference here. We don't need the 10% condition. For experiments. All right, so if you remember, the 10% condition was there because oftentimes when we sample without replacement. Technically, that messes up probabilities. That messes up the binomial, which all this is based off of. But we're not sampling here. All right, so we don't have to make sure that we are sampling less than 10% of the population because we're not taking any samples. We are not randomly drawing people from the population. So we don't need the 10% condition to assume independence or anything like that. So, because we are not sampling without replacement. Okay, so that is one slight difference for experiments. All right, this is only for experiments. If you, like the ones we did in class, if you are sampling from a population, then you do need the 10% condition. All right, time for our calculations. All right, this is the do part. So, our equation here is the same. All right, I'll write it out, the whole thing. It is P1 minus P2, that whole thing, plus or minus our Z star times the standard error for P1 minus P2. All right, so we're going to do this by hand, but then, of course, we will look at how to do it with a calculator. I think it does sort of help us understand where this all comes from if we see the entire math worked out. So what is P1? Well, that is 39 out of 57, and P2 is equal to 43 out of 55. So what do those both give us? Why is that not? Weird. Where'd my calculator go? I am super confused about where my calculator is. Interesting. Well, looky there. I guess I'll use this one then. All right. I'll have to figure that out soon. So what is 39 divided by 57? 68.684. And what is 43 divided by 55? 0.782, let's call it. So first we take and we find what you might think of as the point estimator. What is the difference in those two proportions? 0.684 minus 0.782. Negative 0.098. So negative 0.098. Plus or minus. Now we're going to work on calculating our margin of error. So z star times the standard error. So what is our z star for a 99% confidence interval? So we go menu, statistics. This is going to be a inverse norm. So inverse norm, I'm going to take the easy way out and do 0.99 as a central. Standard deviation is 1, mean is 0. So we get negative or positive 2.576 times the standard error. All right, now of course you don't need this equation memorized, right? It is huge, it is ugly. We're simply going to plug and chug. And of course, make sure you are familiar with just searching up AP Statistics formula sheet, finding the one from the College Board. That is the easiest way, I think, to do it. Come down here, we have the standard error right here for two populations. It is right here. So we take P times Q of the first one divided by N plus P times Q divided by the other N, and then we square root the whole thing. So again, don't need to have that memorized, but make sure you can find it. So 0.684 times the Q divided by 57. I can't do the Q in my head, so give me a second. I'm just going to fill out the general form here at 0.782 times the Q, whatever that one's Q is, divided by 55. All right, so what are the Q's? 1 minus P, right? So 0.684, 1 minus 0.684, and 1 minus 0.782. So 0.316 and 0.218. 0.316, 0.218. So that is our standard error there. All right, so now we just got to start typing this into the calculator. I think I will keep this 0.098 plus or minus. Let's find the margin of error here. And let's type the whole thing in. So 2.576 times the square root of 0.684 times 0.316 divided by 57. Plus, I should be okay here with the order of operations because these two fractions are separated by the plus sign. Divided by 55. All right, throw all that in, hit enter, 0.214. All right, so there we have our margin of error there. It's kind of nice, and that's almost a confidence interval in and of itself, but they do want the interval, so let's actually add and subtract to get our interval here. So we have negative 0.098 plus 0.214 and negative 0.098 minus 0.214. So we are going, so our lower interval here is negative 0.312. And our upper interval, I forgot it already, 0.116. There we go. There is our confidence interval. Now, of course, you can do that on the calculator. If you don't want to do that by hand. I know, right? Who would want to do that on the calculator? That was just so much fun. Bolt, I want to do that all day. So, on the Casio here, I'm going to go interval, a Z interval, 2 proportion Z interval. I want a 99% confidence level. I have this typed in already, but we have 39 successes out of 57 sample size for our first population. And in the second one, we have 43 and 55 total. A 99% confidence level, you hit enter, and it then gives you the interval. Take a look. So 0.116 was our upper and 0.312. So just a slight round off error on my case, but it's basically the same thing. Not too bad. Not too bad. All right, we did the do. Now it's time for the conclude. So what does this answer mean? So we are 99% confident that the difference, or that the interval negative 0.312 to 0.116 captures the true difference of P1 minus P2 which is the difference, and now I'm just going to essentially copy and paste the context, right? Which is the difference in the proportion of patients like these who would report reduced lower back pain after taking naproxen and Valium versus after taking naproxen and placebo for a week. All right, I'm just going to try my best to copy and paste that whole sentence. The proportion of patients like these, don't forget that part, remember my whole speech on that. The proportion of patients like these who would report reduced lower back pain after taking naproxen and Valium. Naproxen, I forgot how to spell that. Which is the difference between that and the proportion of patients like these who would report lower back pain after taking naproxen and a placebo. After a week, right? I know that looks like a lot, but hopefully it's such autopilot. You really are just taking the exact context from the problem as precisely as you can. That way you're not saying more than you are allowed to say. All right, whew, that was part A. Brutal. All right, what about part B? Based on the confidence interval in part A, what conclusion would you make about whether taking Valium along with naproxen affects pain relief? So do we have convincing evidence that taking the Valium does anything? And I believe the answer is no. Because in this interval, what important number is in that interval? 0. 0 is in that interval. So it is perfectly plausible that the difference is nothing. All right, so this is part B. We do not have convincing evidence that adding Valium to naproxen, I'm definitely spelling that wrong, aren't I? Sorry. That adding Valium to naproxen will decrease, I guess will increase pain relief. Will increase pain relief because 0 is in our confidence interval. All right. So it is plausible that there is no difference between taking naproxen with Valium and naproxen with a placebo. Now, if I could spell the word plausible. A couple of things about that statement, all right? Hopefully, first, the logic makes sense. Hey, 0 is a plausible value. 0 is in this interval, so it's perfectly plausible that there is no difference. You have to be careful, though. You do not want to imply that there is, in fact, no difference between the two. All right, you want to be very careful that you don't imply that, oh, there's no difference between these. We don't know that for sure. We just know that 0 is a plausible value. We don't know that 0 is the value. I'm hoping you can see the difference there, that you don't accidentally, in your justification here, state more than we know. We don't want to say that 0 is the value. It is just a plausible value. So we do not have convincing evidence that our treatment is doing anything extra, okay? That's kind of an important idea. All right, I hope that made sense and helped out. Ooh, that was super.